It's truly an honor to present our work here. My name is Fan Yang. I'm a software engineer in the data analytics team at Amazon.
And I'm Yan. I'm an Iceberg commuter and also a software engineer at AWS, working at the same team as Yang. Fan.
So in recent years, the analytics industry has seen a growing demand for fine-grained access control. And Amazon has implemented that feature in some of the services that we provide, including Redshift and Athena Trainer. In the last year and a half, the data analytics team in Amazon worked to support the same with Spark and Iceberg. And the product is currently in preview and going to be launched officially in the coming months. In this talk, we are presenting this product to you. So this talk consists of 4 major sections. We'll first give a brief introduction to fine-grained access control, what it is and why it's needed for data lakes. Then we outline the constraints influencing the design of our solution and summarize the challenges we had to overcome to achieve our objectives. Then we'll dive deep into the details of our design, illustrating how it ensures data security with sample query execution. And in the last part, we'll introduce the work we did to support Iceberg tables in our solution. In order to explain what fine-grained access control is, let me first explain the challenges faced by customers today. Within modern data lakes, data governance typically employs coarse-grained access control. This implies that data owners can only grant permissions to data consumers at the level of entire databases or tables. In many scenarios, this coarse-grained access control mechanism falls short in meeting security requirements. For instance, in the financial services sector, customer account data and financial records are deemed highly confidential. Data consumers may only be allowed to access a small portion of the customer data to comply with privacy regulations. And similarly, in healthcare industry, medical records can only be shared based on the role of the data viewer and patient consent. Such strict requirements cannot be met with coarse-grained access control. And in addition, the vast amount of data nowadays has prompted some organizations to adopt a data mesh paradigm. Under this model, data is decentralized and managed by different domain-specific data teams. A high bar for data security becomes imperative in this context because decentralization expands the number of personas interacting with data. And in this case, it's especially challenging to ensure that a data consumer will not misuse the data if granted access to an entire dataset. And because of these challenges, customers have been urging AWS to deliver a solution that ensures a data consumer can only access the exact portion of data that they are authorized to. So what is fine-grained access control? Fine-grained access control supports several types of data filtering with finer granularity compared to coarse-grained access control. For example, it allows for column-level filtering, where data consumers are only permitted to access specific columns within a table. As shown in this diagram, a data consumer may be granted permission to read the first 2 columns of this table, where the third column, which is considered to be confidential information, remains invisible to the data consumer. Another example is row-level filtering. Data consumers may be granted access to a row only when specific conditions are met. In the shown example, the third row in the table is filtered out by a row filter and hidden from the data consumer. And the cell-level filtering can also be achieved. With cell-level filtering, data owners can restrict access to different columns depending on the row. So continuing the example, the data owner can create a data filter that restricts access to the street address column if the person name is found in a certain list, and allows access to the column otherwise. With fine-grained access control, access to the underlying data sources can be restricted to persons with admin privileges. Data consumers should not be granted direct access to the underlying storage location. Otherwise, all of the security objectives we try to achieve will immediately break. And this helps simplify credential management of the data sources and reduce the chance of credential leak. So listed here are the requirements that we follow in our design. First, the security is a paramount requirement. Our solution needs to prevent both unfiltered data and the access control policies from being exposed to end users. The solution also needs to be resistant to malicious user attacks such as SQL injections and remote code execution. Such attacks may be employed to disclose sensitive information to the attacker, which goes against our security objective. We also need to ensure that our solution does not incur significant performance degradation. An implementation of fine-grained access control would inherently introduce some processing overhead due to the measures that it must take to enforce security. However, we cannot allow it to significantly impair our ability to efficiently process data. And moreover, we want our solution to be financially sustainable for adopters. Hence, there should be no significant increase in the amount of computation required for data processing. And lastly, we like to preserve existing engine functionalities as much as possible. We don't want to force our users to heavily change their applications when migrating to fine-grained access control. Our goal is to ensure a smooth transition while maintaining our security standing. Our solution is built on top of Apache Spark. When it comes to big data analytics, Spark naturally comes into the picture. It's one of the most widely used analytics engine for distributed querying and manipulation of large datasets. It's compatible with multiple languages and supports both low-level programmatic APIs and SQL-based APIs. It has been integrated into several AWS products, including EMR, Glue ETL, and Athena. In the Spark cluster, the entry point for running a job is a driver program. In the driver, a user-submitted program invokes APIs provided by the Spark library to build and execute a job plan. The driver program triggers execution of a dataset by invoking action on the dataset. The execution then starts by analyzing the unresolved logical plan wrapped in the dataset, resolving every symbol to a database object. The resulting analyzed plan is transformed into an optimized plan after running through a set of optimization rules, and then again into a physical execution plan, much like the pipeline in the traditional database management system. Spark further transforms the physical plan into an RDD DAG and sends it to the DAG schedule component, which generates a sequence of stages consisting of parallel tasks. The tasks are further processed by the task scheduler and sent to executors for execution. Each executor performs a subset of the entire job's computation. And depending on the job, executors may read data from data sources, may exchange intermediate data between consecutive stages, and either write the final stage output to a persistent store or stream it back to the Spark driver for subsequent use by the driver program. The Spark architecture imposes several challenges on the design of our solution, mainly because Spark is a library loaded in the user application. The same process that runs user code coordinates the execution of query plans. Hence, the user can replace jars, inject code to the SQL compiler to bypass security policies, and retrieve system credentials which provide full access to the datasets, etc. And the Spark executors are also susceptible to user attacks. Spark allows users to define custom functions and data types, and then use them in dataset transformations. Such user code will be eventually compiled into tasks and sent to executors. The user code can take full control of the user of executors and or intercept system credentials, leading to a privilege escalation attack. A feasible solution also needs to be resistant to the classic side channel attacks, which exploits side effects or command to infer additional information that is otherwise hidden from the user. In database systems with governance features, query predicates can be crafted to reveal either the presence or the cardinality of data hidden by data filters. So here's an example of a row-level filtering defined on a table named employee. The row filter allows users to only see rows having hire date prior to 2006. If user wants to infer the existence of rows hidden by the filter, he can write a query that throws a division by zero error if there are any tuples in the table matching the if condition. To meet our security objective, our design must incorporate techniques to detect and prevent such SQL side channel attacks. Our solution for enforcing fine-grained access control can be summarized in 4 key steps. First, the data administrator defines data filters for a table in a centralized policy store. In AWS, we have a product named Lake Formation that serves that purpose. And these data filters will be retrieved securely with privileged credentials and integrated into the query plans generated from user-submitted queries. The subplans that read unfiltered data from table locations will be executed with privileged credentials. And lastly, a fundamental aspect of our design involves isolating user code execution from the environment performing privileged operations, safeguarding against potential security breaches. And next, we will dive deep into the details of our design, and I will hand the talk to Yan.
Thanks, Fan, for the introduction. So let's look deeply into our design. For our design, the Spark cluster is split into 2 partitions, a user space and a system space. The user space consists of user driver and 0 to many user executors, while the system space consists of system driver and 0 to many system executors. The user space is deployed with user credentials, and the system space is deployed with privileged credentials that can access to the data store for the governance rules as well as the underlying table. Because of this, the system space is the only place that can enforce data governance rules, while the user space is mostly act as a sandbox for user code execution. In our design, the user application will interact with the user driver, and the system driver will act as the actual Spark driver. Here's a different way of representing the same design with the R diagram. As we can see, we're breaking this execution pipeline into 2. When a query comes in, it will firstly start getting parsed and resolved on the user driver. But throughout the analysis phase, it will have to delegate the table resolution to the system driver, who can have the actual access to the underlying table from the database. The system driver will rewrite the query and obfuscate the part that the user is not supposed to know and give it back to the user driver again to continue with the analysis. During the actual query execution, the user driver will again send the entire plan to the system driver, and the system driver will take it from there and process with the rest of the flow. With this separation of the driver and the query execution, this is how we achieve the user application isolation from the Spark driver. Let's give a more concrete example of what we're doing. Let's say that we have an employee table with 4 columns. And data admin wants to define a row-level filter on this table, and they only want the user to see the records where the state equals WA. Or the user in this case wants to run a query to select the hire date from the employee table where ID equals 3. This in Spark can be translated to one of the following approach. Either it's a data frame API, or it's going to be a Spark command. When this query enters our system, it will get parsed and constructed into a logical plan as we shown here. This is nothing different from what is happening in the open source Spark. It will start with the unresolved relation table that is the employee table, followed by a filter operator, which represents the where clause in the user query. Then the upper boundary is the project operator, which is corresponding to the select clause of the same query. However, during the query execution, it needs to resolve the employees table, and this is where the relation gets delegated to the system driver. System driver will then receive the same unresolved table from the user driver. It will then resolve it from the catalog, read from the policy store, and construct a tree like this. It will start with the resolved table as the open source Spark would have, followed by a filter operator. This filter operator is what the data admin has defined for this user. Then we are constructing a security boundary operator on top of them as the root of the tree. And this is a new construct that we introduced that we will dive a little bit deeper in later. Then system driver will give this back to the user driver, though what the user driver will receive is a resolved table relation of the employee. This makes sure that on the user driver side, we can continue with the analysis with the schema required on the user side, so that the columns like ID and hire date are relevant, can be checked to make sure that they are relevant within this query, making sure that this query is making sense. Eventually, when the execution time comes, the entire plan will again be delegated to the system driver. And on the system driver side, we are going to restore the table back to the security boundary that the system driver used to construct. Let's give a more interesting example that we have. In this example, the user query stays the same, but the data admin has a different construct of the policy rule. In this case, the data admin only wants the user to see 2 columns out of 4, the ID and hire date. The user driver will construct the query the same way because the query from the user didn't change. But at the system driver side, things changed a little bit, and this is because the project is getting from the policy from the data admin. Now, because it is a column level filtering, we are having a project that only represents ID and hire date out of the resolved table. Then when we send this security boundary and convert it back to the user driver, at the user driver side, the resolved table will only have ID and hire date, and thus preventing the leak of the other 2 columns that the users are not supposed to see in the first place. Security boundary also has the functionality to prevent unsafe plan optimizations across the boundary. Following the same example that Fan used to have of a divide by 0 attack that an attacker might want to use, they want to have an if statement so that if a record has ID 33, then it will fail the query due to the divide by 0 in this example. However, in our case, we are going to put the filter from the user code outside of the security boundary because they do not belong to the data filtering security filter that the data admin defined. And we are preventing the filtering that the user specify to be applied across the data that are unfiltered because the security boundary layer in the middle prevents optimizer rules from being applied across the boundary. And what the if statement the user specified can only see is the data that they are supposed to see in the first place. This is how we mitigate the side channel attack. Giving a different but slightly similar example, the user can specify user code in their query by defining a user-defined function UDF. And then the user can use this UDF in their query to run the user code that they have. Similarly, in our plan, the filter representing the UDF is again going to be outside of this security boundary, and also again only going to be act on the data after the security filter is completely applied. Security boundary could also disallow filter derivation that exposes access control rule. Giving a similar example of the same data filtering security filter that the data admin defined and a slightly different query. In this query, the user wants to join the table of the employee with another table, table 2, based on the column that is the same column that data admin has defined the security rule on, the state. The right side shows the logical plan that would happen. Assuming that this same plan is running on the normal Spark code that is in open source, this will be something like this without the security boundary as the only difference that we just saw before. And when the optimizer kicks in, it will start triggering a mechanism called filter derivation, which is a well-known performance optimization technique. The join operator in this case will look at both left and the right side and realize that the filter on the employee side is acting upon the same column that the join operator is based on. And then it tries to push the same filter to the table 2 so that when the table 2 data is flowing into the join operator, the filter can be applied so that the minimum data can be transferred. And this can hugely improve the performance of this query. However, this is not going to be an acceptable scenario in our case. This is because the filter under the security boundary is actually the data admin filter, and it is not something that we want to expose to the customer. And if we do nothing, then the customer may be able to monitor and track what has happened against table 2 and thus reveal the security filter that the data admin has defined. Luckily, with our design, this is not possible. This is because of the security boundary that does not pass the filter information to the parent join operator and preventing them from participating in the filter derivation. Despite all the security handlings that it can do, it still can allow some optimizations. In this case, all existing optimization rules can still be applied inside each security boundary. Taking the example that we have on the right side, we have a filter of state equals WA under the security boundary. Underneath the security boundary, this filter can still be further pushed down to the scan operator to, for example, efficiently prune unnecessary partitions, especially if the state is a partition column. In addition, we still also allow the safe operators to be applied and pushed down to the security boundary. Given this example, we have the customer who specified filter equals with ID equals 3 and project of hire date equals another constant. The equality check with constant is a safe enough operator that will not allow any type of user code intervention. And thus, we consider them safe and push them down to the security boundary. This makes our plan the exactly same one as the open source Spark would have, except for this security boundary operator that will perform other important use cases that we will describe further. Now let's talk about physical plan and execution. In our security guarantee, we want to make sure we have executor level separation of unfiltered data processing from user code. This means that the user executors are the only place that can run user code, while the system executors handle unfiltered data and make sure that the data are completely filtered and applied with the security filter that the data admin has defined before escaping from the system executors. We are enforcing our security by a separation of stage, which is the Spark construct that Fan described, based on the operators run within. Let's look at a more concrete example here. So this is the same example that we saw before, and this is the same plan that we just saw. In this case, when the physical planning happens, this plan will be then translated to a stage. This stage is nothing super different from the open source would have, except for the security boundary. The security boundary here acts as an important role because it lets us to know that this stage has to be a system stage, meaning that the executors that are allowed to run this stage has to be system executors. Giving a slightly different example, which is also the same as we had, that the user has a user function in their query. And this will result in a plan like this, where the function from the user is out of the security boundary, as we just mentioned. This will actually do a different thing than what the open source would have. We have to have a security boundary labeled with the system and based on what we just described. But we need to handle the user code separately. User code need to be happen in a user stage. And because of this, we need to introduce an exchange and separation of this entire plan into two stages. This makes sure that the security boundary and anything underneath can be executed on the system executors, while the user code can only be executed on the user executors. And this is how we isolate the user code to user executors. We still have some opportunity for performance optimizations. In this case, we have the example where the user has a query that also contains a user function. In addition to that, they also have a group by clause that can result in an aggregation. If we construct the plan natively, it will be something like this with three stages. One, the same as we speak, it will have a security boundary and assigned to a system stage. And the other one with user code assigned to user stage. And the final one, the aggregation one, because it is only going to be acting upon the data after the filtering, so it can essentially be in any type of stage. However, this is not quite necessary, and we are introducing one exchange while the plan already has the exchange that is required by the aggregation. What we are doing right now is to combine the last two stages into one, so that this plan will continue to only have two stages. And we combine the aggregation and the filter of the user code into one single stage and move the shuffle exchange down. Thus, it is still going to be two stages, and this avoids unnecessary stage separations. What we have talked so far are mostly around query execution, but we also have to do something for the commands. For example, the explain plan is a very popular way for people to see about their query plan and to debug performance issues. While we continue to support that, we need to make sure that the security filter that the data admin has supplied do not get evolved and do not get revealed in the explain plan output. We achieve this by obfuscate security boundary operators to avoid leaking the security rules. We also need to support DDL, but some DDLs are of describe types that can also reveal table metadata. In this case, we're using the unprivileged credential or the user credential to make sure that the data are not leaked. Now, the customer AWS has heavily invested in Iceberg, and Iceberg is actually the only open source table format that this fine-grained access control solution of AWS has today. And there's a lot of customer ask for supporting this on Iceberg, thus we delivered. So in order to support Iceberg feature, we need to work with data source v2 because that is what Iceberg is built on top of. We need to be aware of the data source v2 relation, the different ways of reading the data and the optimization rules. Iceberg also supports time travel query that we need to make sure that our security filter can work correctly with. Despite that our solution today do not handle the write into lake formation support yet, we still need to support write into non-governed tables. And because of this, we need to support delete, update, merge into, and DDLs that are specific to the Iceberg. Iceberg also supports metadata tables. While it is a very useful feature to examine your table, some tables like the partitioned metadata tables and some columns like the stats columns that includes the upper and lower boundary of the column data may reveal information if the data admin has defined access policy upon. And we need to make sure that they are redacted for the tables that are government controlled. Iceberg also supports Spark procedures, but certain Spark procedures, like changelog procedure, will also do the same thing that may reveal metadata information, and we need to make sure that they are blocked for the table with access control rules. And here are the observations and lessons learned we had for the Iceberg integration. Iceberg has a very modular design, which simplifies the extension for the policy store integration that we have. In our case, we need to integrate with the lake formation, and what we essentially need to do is extend some Iceberg AWS module and to introduce additional integration with lake formation. We don't have to touch any single line of the Iceberg core code base. Iceberg also has a data source v2, and its design keeps Spark tasks close to the table object with the implementation of the Iceberg. This is especially helpful in our scenario because with the integration of lake formation requires the credential vending API to be supplied with both the table name and the S3 location. While we have to do something in order to make it be supported with the Spark code base, in Iceberg, this works out of the box. Iceberg also models metadata tables as normal tables, and this hugely streamlines our security control because we can just reuse the same code we have for applying security filters to take action on the metadata tables. So in the domain of access control, we want to bring our learnings to the community through contributions to the development of Iceberg REST spec and its integration with different engines. The native FGAC integration mentioned in this talk so far has been around the integration with Glue Catalog, which is an out-of-box catalog solution for any AWS account holder. However, as we can see, the Iceberg open source is heavily invested in the REST catalog, which offers flexibility of managing and evolving a customer catalog implementation with internal features and optimizations that can evolve independently from engine integration and prevent vendor lock-in. So far, our changes are implemented within the engine in a retrofit type of way, but we envision the support of access control should be a security mode of the engine rather than yet as another feature. We want to fix this problem with the REST catalog so that we can have the access control support as the first level citizen within Iceberg. And here we provide some links to the proposal that we have in the open source, as well as a few email threads, and please feel free to check them out and leave comments. And here we conclude our talk. Thank you everyone for listening.
All right, thank you very, very much. It was very eye-opening, and we actually had a couple questions come in. So I'll bring those up to the idea. Let's see. Ravi asks if one of you wouldn't mind connecting or putting some links in the chat. Those last ones in particular. So if you wouldn't mind doing that, because I don't have access to the slide.
Yeah, let me see if there's a way for me to do that without leaving the slides, because I think if I quit, then it will go away. Or Fan, do you happen to have the same links?
Let me check.
I think I definitely have the first one, but 1 second. Let me get the other two.
I don't have the last two links.
Yeah, can you share the first one? I can share the last two very quickly.
Okay.
Great. Okay. Well, I am going to bring up the first question. So the first question asked around this was, and this was kind of maybe it was 12 minutes ago, so maybe halfway through. Would the new plan with security boundary corrupt the way how Spark decides for the bucketed join or the storage partition join to take place?
So it really depends on where the join is coming from. So if the operators outside of the join, like within the join are partitioned, from the user code, the user query, or the governance rules from the data admin. But eventually, what the security boundary is essentially a passing through layer. It pretty much just connect the upper operator with the lower operator if things permit. So for the performance sake, usually it will not result in a performance penalty.
Okay. I brought on Landon Fairman. If you want to turn on your mic and camera to ask the question you wanted to ask. Otherwise, if you accidentally push the little lightning bolt, feel free to hop off. Next question while we wait for Lena to come in. I joined, so Sumya joined a little late and just wanted to make sure to check about the grant SQL command, or where exactly do you run, basically set this up to configure the security rules. They may have missed maybe the earlier parts. So just as a summary.
Yeah, so for the grant command, actually for this presentation is mostly for demonstrating purpose. For now, we don't have the exact grant command supported, at least in Spark, but this is definitely in our roadmap. I don't know exactly when, but if you are interested in, feel free to share email and we can get it back from our PM input.
Perfect. All right. Do you include a preferred? Oh, by the way, you can do that through the platform without having to share it publicly. You can just directly talk to Yan Yan and Fan Yang and the platform. Just unless you want to share your email with everyone. Do you include a preferred approach for engines to filter columns and rows based on access policies to ensure consistent behavior across engines?
Preferred.
Or is this? It sounds like this is asking like, is there a similar mechanism that could work across, let's say, so EMR, if you had Trino or Presto or another engine, would this mechanism be able to tie into that?
So I think we spend a lot of effort in this solution so that the performance is there and the Spark API compatibilities can be met. Like as Fan mentioned earlier, Spark has lower level APIs and as well as the SQL-based and the data frame type of APIs, and the flexibility in defining user code is something that we really need to protect on. While I think for Trino, while a similar issue exists, and it might not be that prevail, and the user has a less chance of getting filtering into the entire engine. But the high level idea of injecting the security filter through the process that we described is more or less the same. So while the code is not completely the same, it is indeed following the same mechanism.
Cool. Is there a performance penalty for data exchange between like the security kind of server or service and the user execution environment?
So if it is talking about the user driver and the system driver, then yes, there's a slight overhead because the plan has to be serialized into from the user driver to the system driver and getting deserialized. So some penalty in there. And also with the user code example that we had, that we have to artificially separate the stages into multiple, then that definitely becomes a penalty. And also the optimization rules that we talked about, where some rules cannot be applied across the security boundary, then they are indeed also penalties. But those are the things that cannot really be avoided in order to make sure that the security is guaranteed. So we do have some internal benchmark showing this. We have run the TPCDS 3 terabyte benchmark against this versus the Spark that is in open source. And I think in overall, we are seeing like 5% degradation due to various reasons.
All right. We have a follow-up question, but I think you may have answered it. Who would own the security boundary, I guess, in terms of query engine, and could those security boundaries be shared?
This solution is Spark. So security boundary is just yet another operator in Spark. So I'm not completely sure about could they be shared. Like the idea can be shared, but it's a different code base. I'm not sure if I answered that.
Maybe the security, there's like maybe potentially like a live security context that they like. Let's say if you're setting something up with Spark, I think this is kind of getting back to the multi-engine thing. Like if you add a security policy through Spark, does Trino see that security policy?
I see. So the outer layer, which is the catalog or the governance policy, is the lake formation. And lake formation product that AWS has, and lake formation would allow you to define the security rule in terms of the party SQL syntax. So you can, when you are loading the policy, you can load them into your engine. But after that, like what we do in this implementation is pretty much to extend the Spark code base to add the additional operators and do the processing. So that is very engine specific. So we can borrow the same idea to add other engines, but that's what we like. I don't know if we can go easily beyond that without re-looking at the code base of other engines.
Okay, we have a lot of last second questions time coming in, and we're getting close to the end. So this is a quick one. Is there a plan to open source the project like this, particularly this merging this functionality with lake formation in the Spark repo?
Yeah, so we love open source, and we definitely would like to contribute. I think we have the high level idea that we would like to contribute to the open source as much as possible. But for now, I don't think we have a concrete plan on this yet. So maybe like if you share the email or something, that I can get back to our leadership and PM to see if they can answer this question.
And that comes from one of the Iceberg PMCs, Yufei Gu. I think he's Apple, so you can find him pretty easily. Are there? And then this is another coming from another PMC, Russell Spitzer. Are there any issues with resource requirements? Thinking about jobs which may require large broadcasts now would have to live in 2 drivers, as well as task planning for jobs with a very, very large number of tasks. Or is there mostly a drop in the bucket compared to the executor requirements? Let me know if you need me to repeat any of that.
Sorry, I think I lost the last part.
Can you look in the Q&A? Maybe it's better if there's also a visual, and I can repeat the question. Are there any issues with resource requirements? Thinking about jobs which may require large broadcasts now have to live in 2 drivers, as well as the task planning for jobs with a very, very large number of tasks. Or is that mostly a drop in the bucket? Like it's not a big deal. That's a compared to not saying buckets as in real buckets. Russell, shame on you. Is it small compared to executor requirements, which also need to be doubled?
Yeah, I don't think we have seen this as a huge overhead. And also the actual planning, like everything beyond the optimization and physical planning is on the system driver side. So at this point, the user driver is pretty much just waiting for the response from the system driver to get the data back to the user driver. So at this point, the user driver is kind of completely out of the picture, and it's completely the system driver, which at this point more or less act as the open source Spark driver.
All right. Let me see. I think we're getting close-ish on time, but let me try. I'm going to keep going until this thing cuts us off. So would your concepts and examples be applicable for any querying databases, even if the code is not the same? How could we cite your ideas?
Yeah, I think the idea should be can be applied across different solutions. So we are also indeed working internally to publish a blog or article that can also have more information and details and also benchmark results of our data. So please stay tuned.
Oh, that's great. Yeah, share that. If you could share that on the, I don't know if you're on the Iceberg Slack channel at some point, if you could share it there, or on one of the lists.
Not yet at the moment, but
or on one of the mailing lists. That would be great if you could just share it there whenever that comes out. Thank you.
Yeah.
I'm going to keep going. What approach is possible to bring this type of security to end user compute notebooks like Domino, Databricks, or others?
So I think this is a good question. I think we are working on some integration with the end user notebook integration, but for the specific like Domino's, Databricks, I personally haven't have much knowledge on that. So I think it's not going to be hard because you can mostly just interact with the user driver and that's it. But I haven't touched upon the details. So yeah.
Fantastic. That's all the questions that we have. And I just see a lot of appreciation for these ideas, and a lot of people are really excited about it. So great job to you and the team for putting this together, and look forward to getting the article or any kind of research paper you all end up putting out behind this. So great talk. Anything else that y'all want to say before we hop off this session? Nope. Okay, great. All right. Well, thanks everybody for joining, and we'll see you at the next one.
Thank you so much.
Thanks.
Thank you.